Alright, today we're talking about Natural Wonders Chapter 14, and this is all about astronomy. We're going to be starting with the phases of the moon. And moon phases are just something that's really cool. Everybody can look up at the night sky and see these different phases of the moon. And the cool thing about the moon is that the change always takes place from the right hand side moving towards the left. So if we start out with a new moon, so like no moon in the sky, the first thing we see is this small little sliver of light on the right hand side of the moon. This is called a waxing crescent. And that word waxing is just representing an increasing amount of the moon we can see, the bright side of the moon. And the crescent is just talking about the shape, that kind of thumbnail, that sliver shape. From the waxing crescent, we move on to a first quarter. And this is where you can see, it's really a half of a half. So it looks like you're seeing half of the moon lit up, but just remember, we can only ever observe one side of the moon at a time. So the reason we call this first quarter and not a half moon is because really we're seeing half of a half. We're seeing half of the illuminated half of the moon. If you think about it, Earth, somebody always has daytime. Like half the planet is always daytime here on Earth. The moon's the same way. Half the moon is always getting sunlight. Doesn't matter if we see it or not, it's always getting sunlight. So when we talk about the first quarter, we're really just saying we can now observe half of the moon that's getting sunlight. Is that confusing? I don't know. After the first quarter, we move on to a waxing gibbous. Again, waxing means that we're increasing the amount of the bright side of the moon we can see, and the gibbous shape is really almost like that three-quarter shape. It's no longer just a fraction, a small little sliver. It's not half of a half. Now we're seeing 3/4 of that illuminated half of the moon. After waxing gibbous, we get to a full moon, where this is where we're actually observing the entire half of the moon that's getting sunlight. From a full moon, again, the change that occurs with the moon always happens from the right-hand side to the left. So to start out, our waxing phases, the illumination, the brightness, the amount of moon we saw always changed from the right pushing to the left. And now shadow is going to take over from the right to the left. So the first stage after a new moon is a waning gibbous. This term waning just means almost like fading, like the light is going away. And gibbous again is that 3/4 shape of the moon. After a waning gibbous, we have the last quarter. And again, this is a quarter simply because it's a half of a half. This is also where we can talk about this little phrase that might help you remember waxing and waning. It's just that left equals last. If you're looking at the picture, the left-hand side of the moon is illuminated. And anytime the left-hand side of the moon is illuminated, that's the half of the moon we're seeing, it means that we're working towards the last stages or phases of the moon. Left equals last. And then our last phase of the moon is a waning crescent, which this is, again, that little sliver, but this time on the left-hand side. Left equals last. And after this waning crescent, we go to a new moon where we don't see the moon at all. And these moon phases, it's a 28-day cycle. So as soon as we're back to a new moon, the cycle would start over where we would see that small sliver of light on the right-hand side, that waxing crescent start again. After our phase of the moon, we get to a solar eclipse, which this is 3 objects and the relationship in space. It's the sun producing light, the light hitting our moon, and that moon casting a shadow here on Earth. And during a solar eclipse is really the only time we get to observe the atmosphere of the sun, which is called the corona. After a solar eclipse, we have sunspots. And these sunspots are darker spots on the sun's surface. And they're dark because they're cooler. And yes, we're still talking about the surface of the sun, so it's still extremely hot, but they're just relatively cooler than the surrounding areas. And because of that relatively cooler area, it shows up from Earth as a darker spot. These sunspots, they cycle. It's a 22-year cycle where they go from being close to 0 sunspots to their maximum after 11 years, and then they go back down to close to 0 after another 11 years. And these sunspots are also tied to the magnetic field of the sun. The magnetic field of the sun is way more complicated than Earth. Here on Earth, we just have a magnetic north pole and a magnetic south pole, and that's it. But on the sun, there are many, many north and south poles, and this very complicated movement of this electrical field. Our next feature is a solar prominence, and for this one we're looking at that cloud that's kind of streaming off of the sun's surface. And this is described as an ionized cloud, and that really just means it's made of ions. Ions, if you don't remember, they have a charge, so positive or negatively charged. And if this cloud, let's say it's a positive cloud, travels over the sun's surface and it travels over an area that is also positively charged, you know what happens to like charges? They repel. So that means this ionized cloud is forced off of the surface of the sun. But don't worry, it usually doesn't just fly into space, because it will travel over an area of a negatively charged or oppositely charged, and that will pull it back down towards the sun's surface in most cases. Our next feature are solar flares, and solar flares are the opposite of a sunspot. Sunspots are the cooler areas, and a solar flare is an area that's kind of burning hotter and brighter on the sun's surface. So that would be the bright areas that you're looking at in the picture. These solar flares release additional radiation that travels on the solar wind, this energy that radiates out from the sun in all directions, and that solar wind impacts our planet and it hits our magnetic field. And what happens is our magnetic field protects us from the majority of this radiation, and the side of our magnetic field closest to the sun is kind of squished by that force of the solar wind. The backside of our planet, further out into the solar system, the magnetic field gets stretched and pulled, and you're actually seeing that in one of the pictures. And that leads us to our next feature, which are the Aurora Borealis, the northern lights. The northern lights form with an interaction of three different things. Again, it's that solar wind, that radiation from the sun, it's our magnetic field, which you just saw, and it's also Earth's upper atmosphere, so particles, molecules in our upper atmosphere. And what happens is the radiation from the sun is deflected by our magnetic field to our north and south pole. And it doesn't get all the way down to the surface of our planet when it's deflected, but it does get into our upper atmosphere, where it gives energy to molecules in our upper atmosphere, which causes electrons to move up and down, which really just gives off light. And that's what we see with the northern lights, the Aurora Borealis. Man, they're pretty. Our next feature is a comet, and a comet is pretty much just a ball of ice and dust, and it has these very, very large and odd-shaped orbits around the sun, where only for a short period of time it kind of hooks real close to the sun, but then it travels very far out into our solar system, and it's gone for long periods of time. But again, as that comet gets closer to the sun, the solar wind hits the comet, and it breaks off some debris, some dust, some ice, and that debris ends up forming a tail. And comets are known for their tail, but it's really misunderstood. Because there's no friction in space, the tail of a comet does not just trail behind a comet like tying a string to a baseball and throwing a baseball. Of course, the string would travel behind the baseball, but that's because there's friction with our atmosphere. In space, there's no friction. So the tail is actually produced when the solar wind hits the comet. It breaks off material, and it really just forces that material further out into the solar system. So the tail of a comet just simply points away from the sun. So we really can't use the tail of a comet to tell us anything about direction. We can only look at the tail and determine where the sun is located relative to the comet. Our next feature is a meteor shower, and a lot of people call these shooting stars, but it's a meteor shower, okay? And this is just a chunk of rock, mainly rock and iron, that have been flying through our solar system and pulled in by Earth's gravity, and they travel through our atmosphere. And going from a vacuum of space, again, no friction in space, to our atmosphere where there's friction, it makes these chunks of rock and iron heat up. And when they heat up, they light up. Most of these meteors, they never hit the ground, but on occasion, some of them do land on the surface. And the larger ones can be really dangerous and, like, say goodbye to the dinosaurs, but most of the time these small meteors can fall relatively harmlessly without doing any significant damage or extinctions. And that's going to wrap up Natural Wonders Chapter 14. Alright, please make sure you're taking some notes and make sure you're asking questions if you ever have them. Alright, thanks. See ya.